This unit is subdivided into 3 under the category of solution: solute, solvent, and solution. The solute is a substance that's going to get dissolved, and solvent is what's helping the solute get dissolved, and solution is the combination between the solute and the solvent when it's well mixed. This particular video will focus on the solute in itself. Here, let's introduce an image of how a solute gets dissolved. Here is sodium chloride. This is a typical salt, and it's in a large solid chunk form. The Na, or sodium, represented by plus, and the negative is chlorine, and it's chlorine minus, and they're all kind of studied together intact. Soon as it gets submerged in water, you see the water molecule coming towards the negative and the positive charges. Due to the partiality of the partial charges of oxygen and partial charge of the positive and hydrogen attracts the sodium and the chlorine molecule. So you can see that there is a water molecule surrounding the sodium and surrounding the chloride. That surrounding or hydration allows this sodium chloride solid to get pulled away from one another and split into ionic form, where it's sodium plus and chlorine ion. You can see in this chemical equation, there is sodium chloride solid forming into sodium plus aqueous plus chlorine aqueous. What this aqueous means is that this particular ion has been pulled apart from its counterparts, which was the chlorine, and then now it's solvated or surrounded or hydrated by water. So that aqueous helps us to know that this is going to be something that is dissolved in water. Some textbook will write this as sodium chloride and then put aqueous instead of putting it in a split format. But will all solid dissolve in water? Let's find out. These are all ionic substances: sodium chloride, barium sulfate, lead to nitrate. Now, all of these 3 are in solid form S. So if I were to introduce water, the question is, will they form into an aqueous form? So let me draw these arrows indicating that there has been water added with them. And we know from the previous slide that sodium chloride does split off or does go into aqueous format. Or we can write this as sodium plus aqueous plus chlorine minus. This split, we don't usually utilize the word split, but we say that the sodium chloride has been dissociated. So this split means same as dissociated. Well, how did we know? Well, we know it by experience, and also I just told you, but there is a chart to help us understand that it will get dissolved. And this is your solubility chart, also in your reference sheet. Look on the left-hand side of this particular side. Anything that goes under here would be considered to be soluble, meaning if it has lithium or sodium, any group 1 ions, they will be considered soluble, meaning it will dissolve. So on this side, it will dissolve or it will dissociate. Now, on the right-hand side, there is an exception. For example, you have halides. If it has a halide, it will be dissociated. It will be soluble. However, if it has silver or lead 2 or mercury 1, it will prevent it from being split, or it will prevent it from becoming dissociated. So this is area where it remains insoluble. So will not dissociate. And on the right-hand side of this table, you see that there's insoluble compounds right here. And then there are exceptions. Then there will be soluble. So over here is insoluble. On the right-hand side is soluble. So let's try for barium sulfate. Do you see anything here to do with maybe just barium or sulfate? Look very carefully. You can see over here that sulfates are soluble. It will dissociate, but there is an exception. When it combined with silver, lead, calcium, strontium, barium, well, we do have an exception here because it had stuck to that barium. So what this means is that when it's submerged in water, it will not dissociate but remain as solid. So remain as solid. There is no splitting occurring, but in remaining as solid. So we can say this is insoluble. Let's try for lead nitrate. Now we look at nitrate, and you see that nitrate is ions that form soluble compound. All of the nitrate, doesn't matter what, there's no exception. They will all split off, meaning that this will form into an aqueous form, and I will write that down. NO3 to aqueous, or you can write this in a split format, Pb plus 2 and O3 minus, and there's two of them. Let me write aqueous. And this is soluble. So this one is insoluble, this one is soluble, and then we know this is also soluble. Sodium chloride is soluble. And that's because all sodium, right here, can see, and even chlorine are soluble. Now you try the learning check and determine if these following ionic compounds are soluble or insoluble, and come back and check the key. So when these are submerged in water, here, this one is soluble, then insoluble, insoluble, then soluble. Please note that all of these solutes are under the category of ionic compounds. But there are molecular compounds that could also dissolve in water. Take, for example, these chemicals over here. These are all molecular solutes. How do I know they're molecular compounds? Well, I know because these are all made up of nonmetals. Non-metal, non-metal, non-metal. Non-metal, non-metal, non-metal. These are all nonmetals. In the previous slide, over here, we talked about ionic compounds. These contain a metal and a nonmetal. Then when we have metal and a nonmetal, we look at these solubility chart. For molecular compound, however, we don't look at the chart, but we have to look at the structure and itself. This C12H22O11, pretty handful, also known as sucrose, probably you know it as the table sugar. And we have ethanol here, that looks like this. And we have a decane here. Anything that has carbon, hydrogen, and oxygen most likely are going to be a polar compound. This is polar compound. So this one is polar. This one is polar. Carbon and hydrogen, and there's no oxygen. It's just made up of C and H. This long hydrocarbon chain, this is going to be nonpolar. Well, what does this whole polarity have anything to do with solubility in water? These molecular solutes, meaning these are the ones that's going to try to get dissolved in water, are going to try to dissolve in water based on polarity. The greater the polarity, then easier to dissolve in water. Why? Because water is polar. Water is polar. So water likes to dissolve polar molecules. So this sucrose will dissolve in water. So this will dissociate. So this will be soluble. Ethanol will also be soluble because it's polar. A nonpolar here, this is insoluble because if it's nonpolar, they will separate. It will not dissolve very well. So to reiterate, all polar solutes will be soluble in water for molecular compounds. All nonpolar solutes will be insoluble in water for molecular compounds. And learn this rule, like dissolve like. What that means is polar will dissolve polar. So does that mean nonpolar will dissolve nonpolar? Yes, nonpolar will dissolve nonpolar. But right now we're talking in basis of water. Can they dissolve in water? And water is polar, so hence why this rule right here. Polar solute will dissolve insoluble in water. Nonpolar solute will be insoluble in water. Let's do a learning check. It says, which of the following will dissolve in water? First, determine if the compound is either molecular or ionic compound. So I'm going to do the first one, then you try the rest. The first one, I'm going to determine, is this a molecular ionic compound? I can tell that this is an ionic compound, and that's because there is a metal, barium, associated with it. So because there is a metal here, this is an ionic compound. If it's an ionic compound, we use this solubility chart. We see that chlorine, anything to do with chlorine here, and there's an exception, but barium doesn't fall under exception. So therefore, this is soluble. In water, they will dissociate. This is soluble. Now you try the rest and come back and check the key. And here is the key. Something to note here is that when a molecular compound dissolves, even though they dissolve, does not mean they split apart into ionic compounds. They will not form this positive and the negative charge, and that's how it dissolves. But rather, the water molecule will hydrate itself all around the entire compound, allowing it for solvation to happen.